Okay.
It's really an honor to introduce Dr. Lee, and she is one of our very recent PhDs. So she is now Dr. Lee. She graduated from our department, and she got her bachelor's degree in 2014 from Sichuan University in China, and a master's degree of nuclear engineering also in 2016 from NC State here. She is a senior group member of the multi-phase research group led by Dr. Igor. Her research mainly focuses on the high-resolution simulation of boiling phenomena in the nuclear reactor, and the fundamental study of heat transfer mechanism in two-phase flow. During 4-year study, which is very impressive, 4-year study at NC State, she actively involved in the IRT, which is a prestigious form of Department of Energy contract, and it was a project under the name of Development and Application of a Data-Driven Methodology for Validation of Risk-Informed Safety Margin Characterization Model. And she is also involved in the PEST projects. The latest research results are published in several conferences and peer-reviewed scientific journals. And here, talk to us today will be on high-resolution boiling simulation using interface tracking methods. So please join me to welcome Dr. Lee.
Okay. So thank you, Dr. Boram, and good afternoon, everyone. Today I'm going to talk about my PhD work, the high-resolution boiling simulation using interface tracking method. This is the outline of my speech today. First is literature review, and then I will talk about the motivation or the objectives of this work. After that, I will introduce the numerical method we use to do the simulations, and then I will talk about the 2 models I develop and implement in the flow solver FASTA. After that, I will show some simulation of boiling phenomenon using these 2 models, and the last part is the conclusions and future work. So first, thermohydraulics calculation is an essential part of nuclear engineering. In light water reactor, of course, water is the heat transfer medium to remove heat from the core. Boiling among all kinds of heat transfer mechanism it accumulates large heat flux with with relatively small temperature difference, which makes it ideal tool to make it ideal for the applications which requires large which requires substantially heat transfer rates, like light water reactors. But on the other hand, boiling phenomenon itself is complex in nature, and the understanding of boiling phenomenon and modeling of boiling phenomenon remain a major challenge in the multi-phase flow research. And there are different, like the multi-phase flow research has involved approaches of different scales, from like one-dimensional models, the quasi-multi-dimensional sub-channel models, to the multi-phase CFD simulations, and lately the interface tracking simulations. Each of these approaches have its own application range, and it utilized in different scales. The one-dimensional models is capable of doing thermohydraulics calculations for the whole nuclear reactor system, but it relies on a lot of empirical correlations and many of the parameters used in these empirical correlations come from fixed geometries or certain range of thermal and hydrodynamics conditions. So when it applied to the new situations, its predictive capabilities may degrade because the condition is different. And as the high-performance computing power increase, the multi-phase CFD has been used to various of multi-phase flow research, and it's capable of provide detailed velocity and temperature informations adjacent to the wall boundary here, and they also provide the void fraction profile in the 3D domains. But this type of models require certain interfacial exchange term as model closure, and this is one of the cutting edge research as well, and also the validation of this type of multi-phase CFD model is also part of the research, part of the cutting edge research, and. Recently, the interface tracking simulations, basically the direct numerical simulation solver coupled with the interface tracking method, is introduced to multi-phase flow research. This type of simulation, as we could see here, is able to resolve the instant temperature and velocity field at and around interface. You could see the bubble interface here. And it also provides detailed information at local phenomena. It is a great advantage when we want to study the local phenomenon in the reactor subcool channels. Also, it provides a huge amount of high fidelity and high resolution data, which could use to support the development of new multi-phase CFD models and like the physics-based data-driven modelings. And I want to use two examples to explain why we need this type of simulations. The first example is the wall heat flux partitioning. Wall heat flux partitioning model is one of the important model closure for the thermohydraulics calculations. It used to be calculated using the empirical correlation as I'm showing here as an example. The wall heat flux is divided into two parts: the pool boiling heat transfer and the single phase heat transfer. And the empirical correlation, the empirical parameter here is used to determine the contribution from each component. As we could all see here, it's not a true like physical. It's not very physical. And as the understanding of boiling phenomenon get deepened, and this type of mechanical model has been used in the multi-phase flow calculations. And this the wall heat flux here is decoupled to three parts according to the heat transfer mechanism: the single phase heat transfer, and the evaporation component, and the quenching effect. And this model has a better representation of the physics, but it also requires more detailed information about the boiling phenomenon, like the departure diameters, the bubble release frequencies, and the nucleation site densities. So there's where the interface tracking boiling simulation comes to play. Because the high resolution boiling simulations I'm going to present today is able to provide detailed physical descriptions of the local velocity and temperature field. It could provide information for us to get the values like this in the mechanistic models. And the second example is a bubble behavior in the reactor subchannel geometries. Here I'm showing the simulations done in our group. This is bubbly flow in the reactor subchannel geometries, but this is adiabatic case. So, but from this, as we could see here, the bubble is the interface is resolved, so you could see the bubble interface. Also, the bubble is colored with different. The bubble is represented with different colors, and we divide these bubbles to different groups to study their behaviors. From these simulations, we learned that there's a strong correlations between the bubble behavior and the wall distance in the reactor subchannels. And imagine that if we have the boiling model implemented in this interface tracking flow solver, we're able to conduct simulations like the reactor subchannel in the reactor subchannel geometries with heat transfer and evaporation and condensation, which will able to provide more information about the which needed in the thermohydraulics calculations. So there's also why we need the capabilities I'm going to talk about today. And next, I'm going to briefly review the history of these high-resolution Bowling simulations. This type of simulations is started in 1990s. Deere and his group have done a series of Bowling simulations in 2D domains, including the single bubble pool bowlings, the bubble merge, and the saturation film bowlings. But as we could see here, back to that time, the simulations are done in 2Ds. So as the HPC capability increase, the 3D simulation become feasible. And Deere's group has done, here are some examples. Same in the Deere's group, they have done various simulations to study like the bubble merge, the nucleation bowling, and the flow bowling phenomena. But their simulation domain is still very small, and sometimes because of the computational sources limited, only half of the domain is simulated. And nowadays, most of the simulation is done in 3D. Dehiri and Trickinson has done a turbulence bubbly flow simulation with heat transfer, but in their simulations, the evaporation and condensation is not considered. And Sato and Nisano has done brilliant work simulate the bowling regime from discrete bubble to vapor mushroom regime. Like bubble merge, the nucleation side interactions, and are all considered in their simulations, as we could observe here. But all of these simulations I'm showing here is done in the 3D with a structured mesh, which is different from I'm going to show today. For this type of simulation, it have a big challenge when applied to large scale with complex geometry, because the structure mesh is all like cubic or rectangular type. Imagine that when you want to have a simulations with the subchannel spacer grid and the mixing vents, how can you capture the sharp point in the end? That requires different skills, different type of meshing, which is what we are using today, like unstructured mesh. So because they are using, because of the structure grid requirements, their research is limited in the. Their research is more limited in the small scale, like single flow channels or small water pool, and focus on the fundamental study of the heat transfer mechanism. While other simulation tools like could study the large-scale system-level thermohydraulics phenomena, are not able to resolve the interface and the detailed informations like the interface tracking simulation can do. So that's lead to the motivation of my work today. So we want to develop interface tracking model which can conduct simulations with local mesh refinement and structure mesh and highly scalable algorithm for parallel computings. And with this type of model, we are able to integrate the mechanism study on the local bowling phenomenon. For example, use this local effect as a subgrid model, and couple it with the large-scale simulations of engineering applications. And the large-scale bowling simulations enabled by this type of model could help build a bridge between the different scale, from the local phenomenon scale to the engineering modeling skills. And it will help fulfilling the numerical data gap between the local physical phenomenon and the engineering skill interface tracking simulation applications. To be more specific, there are 4 objectives in this work. So first is to implement the Bowling model into the multi-phase flow solver FASTA, and then verify and validate the performance of the Bowling model under various flow conditions. After that, we will explore the potential of this Bowling model in large-scale simulations and engineering applications. And then we want to propose a methodology of information extraction from high-resolution Bowling simulation for quantity of interest. This systematic plot showing the mechanics involved in the Bowling phenomenon. There are 4 main mechanisms involved in Bowling phenomena: the bubble dynamics, heat transfer mechanism, the active nucleation set densities, and thermal response of the heaters. They are all tightly coupled with each other. So if we want to simulate the Bowling phenomenon using the interface tracking method, we have to have a complete description of all these macroscopic of all these physical mechanisms, and couple them in a single Bowling simulations to achieve the large-scale Bowling simulation we dream of. And so in the FASTA, what we did is we describe each of these mechanisms using different type of models, like the evaporation and condensation models, the contango control algorithm, and other like the coalescence and control algorithms. And the color here indicate the different developing stage of this model. So this is teamwork. Next, I'm going to briefly introduce the numerical method we use to do these simulations. FASTA. So FASTA is a flow solver we use to conduct all the simulations I've just showed today. And it's a very powerful multi-phase flow solvers. It's capable to conduct simulations at different scales, like the sub-channel scales or like the single bubbles, like 1 or 2 small bubble scales. Also, it could able to conduct simulations as different flow regimes, not only the bubbly flow regimes, but also the angular flow regimes and also the Taylor bubble scale, or also the Taylor bubble simulations. And the governing equations used in FASTA is 3 conservation law. It's a first principle based solvers. And the interface tracking method used in FASTA is called level set method. Level set method use the level set functions to describe the distance from interface, and the interface itself is set to be zero. Level set, and the property jump across the interface from liquid to vapor is smoothed using a Heaviside function to be smoothed, and the redistricting equations is used to correct the interface while the bubble is moving through the domain. And next, I'm going to talk about the evaporation and condensation models. So there are 2 parts of it. First is the model implementations, and second is the model verifications. In the model implementations, we use a step-by-step approach. So in the first step, this approach will help us to estimate the possible error source in each step. So we will have a better control of we will have a better understanding of the correctness of these implementations. In the first step, we use the analytical solution to generate the phase change volume term, and use this term as a source term in the continuity equations. And this source term is added inside the bubble in this yellow ridge I highlight here. So in this step, we are trying to test the numerical stabilities of this incompressible solver while adding this source term in the continuity equations. And in the second step, where the energy equation is included in the liquid solver, as a large-scale simulation I've showed before, the FASTA the original FASTA is not used to solve the two-phase heat transfer problem. So in order to conduct Bowling simulations, the first thing we need to do is to modify the code to include the energy equations in the liquid solutions. And also the thermal properties for two-phase is also smooth using the same approach, like Heaviside functions to smooth across the interface. And in the next step, instead of using the analytical source term I'm showing in the first step, we're trying to calculate the temperature gradient around each bubbles. In the second step, we include the energy equations in the liquid solution. So we're able to obtain the temperature gradient from the temperature field around the bubble. And after we have this temperature gradient, we're able to calculate the heat flux across the interface, and then convert this heat flux into the volume increase term, and add this volume increase term into the continuity equations to support the bubble growth. So at this point, we have a model like able to support the evaporation and the condensation of the bubbles. And we've conducted the model verifications to test this evaporation and condensation models. The numerical growth rate is compared with the analytical solutions, and it has a very good agreement. So that's the one bubble inside the domain. So let's imagine, what if we have multi-bubble in the, let's say, in the subchannel geometries, and the inlet is subcooled where we have a heated wall. So the bubble in the inlet region and the bubble compared with the bubble like far away from the inlet, they have different temperature field around it. So how can we estimate different growth rate for different bubbles according to their local conditions? That's what we want to solve using these multi-bubble Bowling capabilities. In order to do that, we introduce a bubble tracking algorithm. So this small picture here is showing the bubble tracking algorithm. What it did is try to apply a unique ID for each individual bubbles, as the color you could see here. Different color indicate different bubble IDs. So it tells the code there's which bubble we are looking at. After distinguish this bubble from each other, we're able to calculate the volume increase or decrease term for each individual bubbles according to its own local conditions. And after implementing these multi-bubble capabilities, we also verified these models with this simple two-bubble case. And as we could see here, they have pretty good agreement with the analytical solution as well. And next, I'm going to talk about the counter-angle control algorithm. So why we need counter-angle control algorithm? First is counter-angle quantifies the wettabilities of the solid surface by a liquid. So it's a very essential parameters very essential for the characteristics of the Bowling phenomenon. So we need to have a correct counter-angle in the simulations. But the value of counter-angle is determined by the solid surface, liquid, and vapor properties at macro and nano scales, which is beyond the resolvable scale of interface tracking simulations. So in order to consider this counter-angle effect in the interface tracking simulations, which is like millimeter scale at most, the counter-angle control algorithm is developed and implemented as a subgrid force model. And this plot here showing the pseudocode of this algorithm. First, we set up the target counter-angle, which is determined by the solid surface, the liquid and vapor properties, as we mentioned before. So this is the input. And then we estimate the local current contact angle and the target contact angle, and compare the local current contact angle and target contact angle, and found the difference between them. If the difference between them is smaller than the tolerance, then we say, well, this is okay, and we don't apply any contact angle force. And if the difference between them is large, we will calculate a contact angle force according to this algorithm, and then apply this contact angle force locally around the bubble. And then this algorithm will check the contact angle each time iterations to make sure the contact angle is correct while the bubble is sitting on the wall. And in the next few slides, I'm going to discuss how we calculate all these important terms I'm showing here. First is the estimation of the current contact angle. So the contact angle is defined. The contact angle is measured in the liquid set between the liquid-vapor interface and the solid wall. And in the code, we estimate the current contact angle using the level set gradient. This phi A and phi B are level set. The level set gradient and the wall normal vectors. And next thing is the target contact angle. So the target contact angle we talk about here is not only related to the solid surface and the liquid and vapor properties. It's also related to the velocity of the interface. So because when the bubble is moving along the walls, we could see the contact angle here. The contact angle at each location at the contact line is different. So the contact angle. The target contact angle is estimated using this contact line speed, and is able to give us like a reference value for each time step and to compare with the current contact angle. And if we decide to apply a contact angle force, and this is how we calculate it, it's determined by this delta theta, which is the difference between the target contact angle and the current contact angle. And this is how this force is going to apply at the interface. And if the tolerance smaller than if the difference is smaller than the tolerance, then there's no force applied. And if it's larger than the tolerance, and we'll apply a force according to the difference between these two. And after implement these models, we perform the model verifications as well. So the first thing we test is critical contact angle. So imagine a bubble is sitting on the walls, and we perform a force balance analysis on this. As this contact angle change, there's a critical point where we'll keep the bubble on the wall, where any value is smaller than that will cause a departure from the wall. And this is the value we want to compare in this test. For this specific examples, the analytical critical contact angle is 41, and then we simulate this. We simulate these bubbles using FASTA, and try to control the contact angle using the model we just implemented. And this is the three values we try: 35, 40, and 39. As we could observe here, when the value is 35, the bubble will departure because the contact angle is decreased to 0. And when it's 39, it's also departure. When it reach 40, and it stay on the wall. So we prove that we are able to predict this critical contact angle as the analytical solution shows. And the second test is about the target contact angle. This is another K parameters used in this model. So for the target contact angle, we want to know, as we given a certain target contact angle, does the code able to maintain the same value we gave it? So we have tried 4 different values, the 20, 30, 40, and 50. And because the critical contact angle is 41, so any value like smaller than this will cause a departure, as we observe here. But when the target contact angle is 40 and 50, we could see that the bubble is stay on the wall, and the code is able to maintain the correct contact angle. And this is match sensitivity studies we've done for this target contact angle. If you are familiar with numerical method, you know like the match sensitivity studies we always do to make sure the numerical method is correct. And then I'm going to show some results conduct using these bowling models. So first part is about the pool bowling simulations. The first case is single bubble growth and departure from the wall. This case, we try to demonstrate the couplings between the contact angle control algorithm and the evaporation and condensation algorithm. As I said in the very beginning, one of the difficulty here is to coupling different mechanism in the same single single bowling simulations, and so this is we try to demonstrate here. As we could observe here, the bubble is growth, and then it departs from the wall, and there's quenching effect in the wake region of these bubbles. And again, the match sensitivity studies. The bubble's supposed to move, okay. And from the result, we could see like this algorithm is able to it have good mesh convergence for different meshes. The next case is nucleation bowling from a single site. The setup here is very similar to the first case, but the difference here is we have a small dent on the wall act as the artificial nucleation site. After the first bubble departure, a small piece will left in this nucleation site act as the seeding bubbles and suppose the new bubble grows from the same site. And here we have a superheated bottom wall with 5 superheat and subcool top walls. And the inlet-outlet boundary conditions is applied here, try to compensate the volume change inside the domain. Because this is an incompressible solver, so when the water is become vapor, there's a huge volume increase. This inlet-outlet boundary conditions is help us to maintain the balance inside the domain. They're supposed to play. Yeah. Well, yeah, this is supposed to be a video, but anyway. So the next case is a validation case. It's same as the previous cases about the nucleation bowling, but here we try to compare it with the experimental-based correlations. Let's not play again. Well, it doesn't like me, so it's no movie. But anyway, the result is so I able to extract the bubble departure frequency, which is 1 over the bubble departure time, and compare it with the experimental-based common use the bubble release frequency model. And this purple point is a numerical result. And this has pretty good agreement with the correlations. And next, I'm going to show some flow bowling simulation results. First is a single bubble flow bowling simulations. We try to validate it with the experiment result. Again, this is a video, but it's not playing. But this is the experiment pictures I get from the literature. And as we could observe here, the departure time and the bubble shape is very close to the experiment. And we also compare the bubble growth rates with the experiment data as shown here. And this has pretty good agreement as well. Well, the previous case I've shown before is all about single bubbles, and the last case is about the multi-bubble flow Bowling simulations. We have two parallel plates and the periodical boundary conditions on the side wall, and claim the plates act as the obstacle inside the domains. Here we try to represent a very simplified spacer grid and missing vents. And the inlet is subcooled, while there's a small heating patch under these obstacles. And we are trying to place several bubbles inside the domains. Because the existence of these obstacles, we expect to have different local velocity and temperature conditions, and we expect to have different bubble behaviors due to these local conditions. First, we conduct single phase simulations and pick the bubble locations. As we could imagine here, this is the subcool inlet, and the first bubble is placed in the subcool regions. And because there's a heated surface and there's a thermal boundary layer grows on this wall, and in the weak region, because the existence of these obstacles, we have induced turbulence in the weak regions, and it hence the mix of the temperature and heat transfer rate. The second bubble is placed under these obstacles and in the center of this heating patch. The last bubble is placed in the region where it has the highest superheat. And in the top regions, we observe these locations where the local velocity here is smaller than the other locations. This is where we place the fourth bubble. We expect to see if the low velocity is around it will affect its departure. It's not playing, but at least we could see this is fully developed single-phase results, the temperature distributions, the thermal boundary layers, and the superheated regions. And this is the low velocity regions on the top. So that's the advantage. Like even though we couldn't see the videos, we are able to extract information from it. So we extract the growth rate of each bubbles and also the superheat around it. As we expected, the third bubble, which has the highest growth rate, and the first bubble condenses very quickly because it's very near to the subcool inlet. And the second and the fourth bubble grows a little bit, but it doesn't, and then start to condense for this bubble when it reaches to the subcool regions. So yeah, so that's what I'm going to show today. This is the conclusion. So during my PhD, I was able to develop and implement these Bowling models in the multi-phase flow solver FASTA. And the contango control algorithm has been successfully coupled with the evaporation condensation algorithm. I brought the bubble tracking algorithm into this evaporation and condensation model as well. The model verification and validations has been done for these Bowling models. And we also explore the potential of these models in pool bowling and in simulating pool bowling and flow bowlings. And the multi-bubble flow bowling simulations show the potential of this current model in solving bowling problems with complex geometry. So in the future, we can conduct like large-scale bowling simulations as I showed in the very beginning using these bowling models. And yes, that's all I have today. Thank you.
Thank you, Dr. Reed. And now we have time for any questions. Please, questions. Yeah.
Why do we need a high resolution code like pasta that could resolve to the scale of each single bubble? Why do we need such kind of code?
So just as said in the very beginning, first there's no other approach we could use to study the local phenomena in the reactor coolant channels, especially when we have all these structures like spacer grid and mixing vents. And this approach could to help us to understand what's going on under these regions. And the next reason is because the next is because, for example, we're using the multi-phase CFD simulations to help us to do the thermohydraulics calculations. But this type of model requires a lot of model closure, like bubble release frequency, bubble departure diameters. This type of parameters is hard to obtain by the traditional experiment approach because it's very hard to conduct simulations in the real subchannel scales and under the PW and BWR conditions. And this type of simulation could help us to extract information like that.
Questions? Questions to Dr. Reed? Yes?
You should result for simulated for single bubble departure. So is there any capability for intensive boiling?
Intensive boiling, you mean like?
Several bubbles departure consequently.
Yes. I'm not showing here, but we have done some simulations on multiple nucleation sites. Yeah, I wish I could show it here.
Any other question? Well, I have a question, but I will wait until he asks. Okay.
Did you verify your result with the experiments?
Uh,
Results or any other kind of comparison with other people's results?
We verify the bubble release frequency with the common use correlation like the Zuber's correlations and the Jacob correlation. And we compare the flow boiling results with the experiment.
Any other question? My question is about, how gravitational effects are included in the simulation. In the set of equations. Gravitational effects.
Oh, gravitation. Yes, the gravitation is considered in all the simulations I've shown.
Only in the vertical piping or also in the horizontal?
In the horizontal and the vertical, both. Yeah, both.
Okay.
Yeah. Sorry, I should mention that.
Yeah, I just wanted to make it clear that the inclusion, because you showed the momentum equation and you put the convective derivative, and then to the other side I see the gradient of the pressure, and then I said, okay, what is the gravitational force here? And so, I think that it is included already in the set of equations and in the simulation for both horizontal and vertical piping.
Right, yes.
Right?
Mm-hmm.
Right. Any other question other than my, yes, please.
Is there any penalty to scaling with your new implementations to FASTA?
For now, we've tested this, we tested in the Argonne National Lab, like 1,024 processors, I think. Yeah. So far, we don't have any concern about the scalabilities of this model.
Any other question? Yes.
Another one. So
Please, go ahead.
for the single bubble simulation,
Right. Yes. Like I mean, that's what one thing we are trying to do. We are trying here is how to use the high resolution data more efficiently. But here's like the. But I want to emphasize here is. Yeah, you mean like this point? I want to emphasize here is this is a validation case. So we try to make sure our model is correct. We compare it with correlations. Because the correlation only given 1 point. So we have to somehow convert the high resolution simulation data to 1 point to be able to compare with the correlation.
Any other question? I'm seeing one of the references that goes back to 1931, which is a German one. Right here, Jacob and Fritz.
Oh,
Yeah.
yes.
So it's still valid that really some of the very old references are really fantastic and that they are valid for being used, because here you have in 69 you have the correlation of bubble to partial diameter, right? And in 59 you have the hydraulic aspect of boiling heat transfer, and it was the thesis back in 59.
The reason I use this correlation here is like sometimes it's hard to find like experiment data to compare with in the literature, and that's what we can do here. So the next step is try to contact some experiment group and to get more data from them, so we could do direct comparison.
Any other question? All right, let us thank Dr. Lee again.
Thank you.